There are instructions under the general Slack channel for submitting your poster to the website. So it can be displayed there. So please go ahead and utilize that. As a reminder, please submit your questions to Slack channel 5B by replying to the appropriate talk title. I've been instructed to use the number of upvotes as guidance. So if you like a question, you want me to ask it, please use the thumbs up icon. And our first speaker is Enrico Garaldi, and he's going to tell us about first results from the MoRiA simulations.
Yeah. Okay, thank you. Thanks for organizing these much needed scientific gatherings in these times of social isolation. And actually, for once, I'm quite happy to be talking toward the end of this conference, because my talk is more focused on what is, in my view, the future of numerical simulation at the epoch of reionization. So this is my attempt, actually our attempt, because it's not my lone effort, but it's together with Rahul Khanna and Aaron Smith mostly, but many other people around the world, to build what we think is the next generation of numerical simulation. So as you see from the title, these were supposed to be called the MoRiA simulation. We spent quite a lot of time thinking about a nice acronym we all liked. And then just a few days ago, we realized there is one single paper in 2017 that uses the same acronym. And so we decided to change. And these are now the Tessan simulation from the Etruscan goddess of light. Okay, so what are these simulations? Let me start with a plot that was discussed actually yesterday. This is the cross-correlation between the Lyman alpha transmitted flux along a quasar sight line and the position of galaxies around these sight lines. Romain Meyer did a very nice job in explaining all the details of this. What I want to point out here is that in a previous attempt that I published last year, I tried to reproduce this feature, this enhanced transmitted flux at intermediate scales from the Croc simulation, and I failed. The simulation here are the white lines, and so as you can see, there is missing flux. Now, this, together with many other scientific drivers, brought me and my collaborator to think a bit what we can do to improve on current simulation. And the problem here is that these simulations are now so expensive that we cannot just afford to explore the parameter space. And so we need to try to be a bit smart. So to explain you what we decided to go for, let me just pull up this picture. You have seen this hundreds of times. I'm not gonna explain it. What I want to point out is that numerical simulation can be categorized in two different classes. One is where the majority of them are simulation focused at low redshift, for example, Illustris, Eagle, and so on. And by focus, I mean that they are calibrated and run and tested at low redshift and often miss the physics to explain the high redshift. On the other hand, the simulation that focus on the high redshift and on the epoch of reionization in particular often have all the physics needed, but they are rarely tested all the way to redshift 0. There are obviously exceptions to this, but I think there is a missing connection many times between these two, between early and late universe. And so this is one of the reasons why we are devising a new simulation set. We are trying to bridge this gap by using a galaxy formation model and dust model that were developed and tested at redshift 0. So they have been thoroughly tested, and then we complemented them with the radiation transport needed to study the epoch of reionization. This model is the Illustris TNG galaxy formation model. Just briefly, it builds upon the Arepo moving mesh code as mass, energy, and metal return from supernovae in the AGB stars, explicitly tracks 9 metal species, as magnetohydrodynamic, bimodal black hole feedback, and stellar winds. So what is missing to study the epoch of reionization is obviously radiative transfer. This is just an overview, though, of the many properties that the TNG model can reproduce at low redshift. So we can build upon a model that is able to reproduce a large variety of observed properties where the observation have exquisite quality. But we need an extra piece of physics, and this is, as I was saying, the radiative transfer. So Rahul Khanna actually implemented a moment-based M1 closure method in Arepo. We have photons from both stars and QSOs and multi-species non-equilibrium chemistry. And the bottom right, you can see that this method is not only precise, but also actually quite fast. So we only not only quite fast, but also precise, with only 32 squared cells or resolution element, we can reproduce what Ramsey RT yields with 1024 squared cells. And the other piece of physics that we included is dust. So the dust model from Ryan McKinnon, again, was tested thoroughly at redshift 0 and performs well. You see the dust mass function compared to observation on the bottom right. And so we just take this model and implement it in the simulation. We don't touch any of the parameters. So in this model, we have dust creation from stellar yields and grain growth, and dust destruction from supernovae and thermal sputtering. But we also want to bridge the gap between large boxes needed for the statistic and the high resolution needed to study the details of the galaxy. And so we use this simulation strategy. We focus most of the computational time on a large box simulation of 100 megaparsec on a side, 10 to the 6 solar masses in dark matter resolution, complemented with smaller runs where we explore physics, say the escape fraction models, early versus late ionization, and so on. And then we pick object of interest where we zoom in, including extra physics at the smallest scale, for example, going beyond the equation of state approximation that was discussed yesterday, or studying the Lyman alpha radiative transfer, like Aaron Smith showed yesterday in his talk. And finally, we want also to bridge the gap between simulators and the community, and so we plan to make all the data available once these simulations are finished. One last bit of technical detail, we use fixed initial condition, which means that unlike normal initial conditions, we don't sample the power from a Gaussian distributor centered on the expected value, but we exactly fix the power at each and every k to the expectation value. This basically means we are sampling the average universe, that not only has the average density of the universe, but also the average power spectrum. This has been shown to suppress a lot the variance, but not affect any of the statistical properties. Okay, so this is the mandatory movie from the simulation. You see dark matter, gas, and stellar densities on top, H1 fraction, temperature, and photon density on the bottom. So you can see the reassuring picture of ionized bubble that emerge from the first objects and then percolate and create a re-ionized entire universe. So let me just focus on two of these panels. One is the ionized hydrogen one. So from here we can get the ionization history of the universe, and this is the only, this is the quantity that we use to fix the only free parameter in this model, which is escape fraction. And once we fix this escape fraction, everything else comes out naturally from the model. So I'm showing here the UV luminosity function for galaxies at 3 different redshifts, 6, 7, and 8. And you can see that our simulation, which are the solid lines and the shaded region, actually reproduce quite well the observation, which are the symbols. So in this case, for simplicity, we have just included an empirical dust correction. But as I mentioned, we can do better because we have dust. And to show you what dust does in the simulation, I've plotted here the dust mass versus stellar mass. The blue points are from the simulations. The lines are the median and 1 sigma around it. And the symbols are, again, measurements from observations. And so you see that in the high mass end, where our simulation overlap with available constraint, we are actually doing quite well. On the right-hand side, we have the prediction from the dust to metal ratio as a function of metallicity compared to some of the models available. So we seem, for example, to match quite well with the Vijayan 19 model. But what I want to show is that we do not only have the statistics to look at these galaxies, but we can zoom in. And actually, I forgot to say at the beginning, all the results I'm showing are based on a simulation or a calibration run, which is a factor of 8 away in resolution from the target one. So you can see that we can pick the largest object in the simulation, for example, and zoom on it and still see a lot of details. We have the gas density, gas temperature, dust to gas ratio, and neutral fraction in these panels. So you see the quantity of details that our huge numerical effort actually brings up. Okay, so this is a laundry list of what we want to do with the simulation. We go from the Lyman alpha spikes to galaxy correlation, which was, as I said, one of the drivers of this simulation set, to 21 centimeter galaxies correlation, high redshift dust and magnetic fields, because I just mentioned that in passant, but we have magnetic fields in this simulation. As Aaron showed yesterday, Lyman alpha radiative transfer, high redshift metal lines, because we have metal tracking, so we really know how, like, the relative abundances of metals. And then let me just mention that when you combine MHD and radiative transfer, you actually can explore new magnetic field seeding mechanism. I don't have the time to go into the detail, obviously, but if you have any idea, please talk to us. This is an ongoing effort, so we are very open to any suggestion and idea. Before concluding, let me just spend 1 minute on a different effort I've been working on, or a different thing I've been working on. This is called CoreCon. Just came into being from the randomness of my collection of constraints. I had them scattered around different computers, different folders, and at some point I decided to homogenize them in the units and in the format, and so this became a Python package that is now available. You can install it, you can look at the documentation online. And most importantly, I decided to make it as easy as possible for people to add their own constraints. So if you have any constraint related to the reionization, you can just go or look at the documentation and put in your constraint. With that, I just leave here the summary and take your questions. Thank you.
Thank you, Enrico. So Sultan Hassan asks, do you run RT on a grid or particles, like C2 ray or like traffic, and how fast is it?
Okay, so we run on the RT on the Voronoi tessellation that is used by a repo. So it's a grid, but it's not a Cartesian grid, it's a Voronoi tessellation. This is moment-based, so you basically treat you solve the moments of the radiative transfer equation. Regarding the speed, well, it's radiative transfer, so it's slow, relatively slow. So just to give you an idea, is roughly a factor of 4 slower than the hydro part, which is actually quite great. I would say, but also this depends a lot on the resolution and on a lot of technical details. So depending on the, for example, on the simulation box, it will change a bit.
Okay, Chris Lovell says, looks amazing. Do you run the same initial conditions to z equals 0 with less physics to see what the descendants are?
So as I said, this is still an ongoing effort. We definitely will do that. We haven't yet. We have run, sorry, go ahead. I just want to mention, I forgot, we had made comparison to down to redshift 5.5, running with and without RT, so the original model and ours. We haven't still run till redshift 0, but we'll definitely do that.
Okay, Aswin Bijayan asks or says, really nice talk. What changes do you get from TNG on adding RT and active dust? Also, what attenuation curves do you get from the dust distribution in the simulations?
Okay, so regarding the differences, we don't get actually much difference. So very small differences in the smallest galaxies, but I should say that we are still a factor of 8 away from the target resolution. And the target resolution is the minimum resolution to resolve these atomic cooling halos. So we don't expect, we expect to get more difference, more differences when we reach the target resolution for our simulation. So I will hopefully answer that question in a few months. So the other one was the attenuation curve. I don't know yet. As I said, so this is more about the future in the sense that this is the plan. We have run some tests, but yes, we haven't actually carefully looked into that yet. But thanks for the suggestion. I will definitely do it.
There's one more question to address on Slack, but we have to move on to the next talk.
Okay.
So our next talk is Feige Wang, Evolution of Reionization-Era Quasars.
Hello, everyone. I'm Feige Wang, a postdoc at the University of Arizona. First, I would like to thank for organizing this wonderful virtual meeting, because in this time, we cannot go to observe this meeting. We cannot travel, and this meeting gives us a great opportunity to catch up the latest studies. So today we'll focus on the Reionization-Era quasars. Really find the rest of 8 quasars in the next coming years, and what kind of environment this quasar residing in, whether residing in the most overdense environment or a random field. Okay, so in the last couple decades, we have a good understanding of the density evolution of quasars from redshift 0 to redshift 6. Like the density peaks at redshift 2 to 3, and the drops and declines very fast from redshift 3 to redshift 6. But we have little information at higher redshift. That's one of our motivation. How to find those quasars? Since the discovery of quasars, there are many different techniques to find the highest redshift quasar. In the early time, people using the radio technique, and then followed by optical. But if you go to Reionization-Era quasar, you have to use the infrared because the Lyman alpha line redshifted to close to 1 micron or even beyond 1 micron. So we really needed the infrared wide imaging surveys. Fortunately, in the past few years, there are many imaging surveys. I will not go through each survey, but these surveys provide us a 20,000 square degree of the sky with infrared imaging, and our selection are based on this. I will not talk about the selection details. I will go to see the results directly. I wanted to first highlight 2 discoveries made by us very recently. One is the redshift 7.52 quasar. We just published this quasar EPG letter in last month, and it has a wonderful Hawaiian name, Continuum, which means the unseen spinning source of creation surrounded with brilliance. This quasar hosts a 1.5 billion solar mass black hole and challenging the black hole growth history. And the other quasar is discovered very recently, which is a luminous quasar at redshift 7.62. And here shows the 2D spectrum of this quasar. We can clearly see the Lyman break at 1.05 micron. So this is the new quasar redshift record holder. Besides this really high redshift quasar, we already have a relative sizable quasar sample at redshift beyond 6.5. To date, there are about 60 quasars at redshift 6.5, allows us to do some statistical studies, and among them, 8 quasars at redshift beyond 7. So among those quasars, more than 30 quasars discovered by us, and 5 of the 8 quasars at redshift 7 beyond 7 are discovered by us. So this is a really good opportunity for us to do statistical studies. But our selection currently is not complete at a really high redshift, but it's relatively complete from redshift 6.5 to redshift 7. So we can really, for the first time, to measure the density of quasars at this redshift. Here shows the quasar luminal function we measured based on this quasar sample. As shown in the orange dotted orange line and the dots. I also show the redshift 6 quasar luminal function here. As a comparison, you can see that the density or the normalization of luminal function declines a lot, which means the quasar density drops very fast. So if you integrate the luminal function, you got the density evolution. That's our measurement. It's about 0.4 per gigaparsec cube. So from this plot, you can see that the decline rate seems increasing towards to higher redshift. If you extrapolate this decline rate to higher redshift, that means there are only 1 quasar in the observable universe at this brightness. So we really wanted to find those really first quasar host billion solar mass black holes. How to find them? Fortunately, there are several surveys in the coming years will provide a excellent data set for finding those quasars. The LSHT survey will allow us to find out several thousand quasars at redshift beyond 6, and about 100 quasars at redshift beyond 7. But if you wanted to go higher redshift, you really need the infrared survey from the WFIRST or the Raman telescope and the Euclid telescope. But even with those surveys, we can still only find like an order of 10 quasar at redshift around 8. And we probably can find one quasar at redshift 9, or we probably cannot find them if the decline rate is keep increasing. So we really want to find those quasars in the next coming year with these new surveys. All right, so since the quasars density is so low, they must reside in the most Bias halos, and this should be residing in the most overdense environment. So how to probe the environment of those quasars? There are many efforts in the past couple of years to study the environment with both HST and the ground-based imaging to searching the Lyman break galaxies around quasars. But the HST field view is too small. It's much smaller than the size of a protoclass, which could be even up to several tens megaparsec. The other problem is the Lyman break galaxy redshift uncertainty is pretty large, so the signal is washed out by large projection effect. And also, if you only target few quasars, it's strongly affected by the cosmic variance. In order to solve these difficulties, we can do the deep wide field imaging, and we can use the narrowband imaging rather than the broadband selection to narrow down the redshift of the galaxies, and then to pick up the galaxy directly related to the quasar. There are several works done recently, but as we have already seen that from GT's talk in this morning, the quasar broad lines usually has a really large blue shift, so they cannot represent the systemic redshift of the quasars. If you do not have accurate redshift, which means you probably can miss the really Lyman alpha emitters close to the quasar, like here. So two examples. This is a quasar real redshift, but initially before doing the narrowband imaging, the redshift is here. So the real Lyman alpha emitter is close to the quasar is actually out of the narrowband, so you miss all the overdensity. And also we needed to do a larger quasar sample to do the quasar galaxy cross-correlation function to finally give an answer of the environment of those distant quasars. So in order to get the accurate redshift, we are surveying the C+ line from the host galaxies of our bright quasars at redshift beyond 6.5. Here, so some examples. And fortunately, we got about more than 10 quasars can be probed by the narrowband imaging. We have done one observation for one quasar at redshift 6.63. As shown here, the Lyman alpha emission of the galaxy at the quasar redshift is right in the center of a narrowband, and then we can select the Lyman alpha emitters. We are using the Subaru to do the really wide field deep imaging. As a comparison, here is the HST field view. Here is the size of the full moon. So we are going down to about 25.5 magnitude also. And we really pick up overdensity. We really find it's overdensity surrounded by the quasar. Here is the central quasar. This map is the density map of the Lyman alpha emitters selected using the Subaru HSA imaging. So you can see that the density is pretty high at the center, and the scale is really large. If you like only using HST coverage, it could miss the overdensity. And we also observed this quasar field with many other observations, the G70 dust continuum observations and the ALMA observations to get the C+ line of the galaxies in the quasar fields. As shown here, we have already discovered several galaxies at redshift close to the quasar, so which means this quasar is really residing in a very overdense region. This is our first example. We are designing a new filter to cover more quasars, which will be hopefully installed on this fall, and then we can study more quasars to finally get the cross-correlation function between quasars and galaxies, and to answer the question whether the quasars, the highest quasars, residing in the most overdense environment. Okay, I will summarize here. The quasar spatial density declines really fast, but we already have a statistical quasar sample at redshift 7. We have already used this quasar sample to study the density evolution. We have used this quasar sample to study the IDM neutral fraction, as shown in Jin Yang's talk yesterday. And we now discover a new quasar redshift record holder at redshift 7.6. And we identified a large scale overdensity around the luminous quasar at redshift 6.6. Yeah, I will summarize here. And then thank you for your attention. I will be happy to take any questions.
Questions for Feige? Rebecca Bowler asked, can you say anything about the host galaxy of these bright quasars?
Yeah, sure. So those quasars, the host galaxy of those quasars are relatively bright, like it hosts the star formation rate, and the star formation rate of those quasars are about several hundred solar mass per year, and the total dynamic mass could be 10 to 11 point something solar mass. But currently our resolution is not high enough to study the kinematics, but we do see some really nice velocity gradient of some of the quasars. So yeah.
Okay, Seiji Fujimoto asks, how many targeted quasars at z equals 6.6 show the overdensity?
So currently we only target one quasar. So we will target more, and I can answer you this question in the next few years, I think.
Alyssa Drake asks, signs of carbon-2 outflows?
That's a really good question. So from the individual observations, like the C+ line of individual quasars, we did not see any evidence of the outflow, but we are trying to stack all the C+ spectra of these quasars, and hopefully we can see some outflow signature. But based on the UV lines as shown from GT's talk, those quasars could have really large outflow or driving by the radiation, but I'm not sure whether we can see the C+ outflow.
Okay, so Jarit Mati asks, I know it's low number statistics at redshift 7.5, but is there a selection effect against redshift 7.2 to 7.5 quasars? For example, a combination of available BV filters.
Yeah, that's a really good question. So currently, like at redshift below 7, we are quite complete and there's little bias, but at redshift higher than that, we do have some bias because those 7.5 quasars, like the dropout, its dropout is optical. You basically see nothing in all the optical imaging. But for quasar at redshift 7.2 also, you probably can still see some flux in the Z-band or pan-star Y-band. So for such kind of quasar, we haven't followed up yet. But we are mostly focusing on the totally optical dropout. So at the redshift beyond 7.2, we probably have some bias to 7.5 quasars, and we missed some 7.2 quasars, but we will follow up them later.
Okay, and Fabio Vito asks, can you share the ID of the QSO of which you study the environment? I think I missed it.
Sure, I didn't put it in the talk, but I will send you the ID later.
Okay, thank you. So our next talk is Joe Lewis, Extinction and Dust Escape Fractions and RHD Cosmological Simulations of Reionization. This is Joe here. Okay, I guess Joe isn't here. Let's move on to the next talk, which is Xiangcheng Ma on the escape of ionizing photons from high-redshift galaxies, insight from realistic cosmological simulations.
Okay. Thank the organizers for this wonderful work conference and for giving me the opportunity to present my work. My name is Xiangcheng Ma. I'm currently a postdoc at UC Berkeley. I work on cosmological simulations of galaxy formation. So the escape fraction of ionizing photons is one of the key parameters for understanding cosmic reionization. If we believe star-forming galaxies are the dominant sources for cosmic reionization, like we see in this cartoon picture at the bottom of the screen, during the epoch of reionization, each galaxy creates its own ionizing bubble, and these bubbles expand and overlap until reionization finished. And if you look at inside this bubble, like the cartoon picture I show on the top right corner here, we know the ionizing photons are emitted from massive stars in the first place inside these galaxies, or OB stars in these high redshift galaxies. The photons need to, is there a problem? The photons needs to go through a lot of traffic before they can actually get to the IGM to reionize the universe. For example, there's star-forming clouds around these massive stars or in their stellar medium and multi-phase circumgalactic medium. A lot of things going on in the CDM particularly. So it's a very complicated and multi-scale problem. So in this talk, I will define escape fraction simply as the number of ionizing photons escaped outside the Beer radius divided by the number of ionizing photons emitted by the stars. So we start to use cosmological zoom-in simulations to study this problem since a few years ago. This is just a one slide brief review about our old results. In this 2015 paper, we used 3 simulations from the previous generation of the FIRE simulations, run to redshift 5 to 6. The halo mass is from 10 to 9 to 10 to 11 solar masses. We find a key physics here for the ionizing photon escape fraction is the competition between stellar evolution and the time scale for feedback to disrupt the burst cloud around these massive stars. For example, as this plot shows, stars of 1 million years old are almost embedded in the burst cloud. Nothing can escape from this region. You need a few million years for stellar feedback to destroy the burst cloud before the ionizing photon can escape. However, a few million years is already the lifetime of massive stars. By the time the photon can escape, there is no longer many ionizing photons available from the stars. So we find on average escape fraction is below 5%, which is not very good for cosmic reionization. But one possible solution is to include binary stars. If the binary stars can produce more ionizing photon after 3 million years, they can increase the escape fraction by a factor of 4 to 10. So this is just some of the old results we had a few years ago. But I want to introduce this product I've been leading in the past 3 years or so. It's a suite of 35 cosmological zoom-in simulations of galaxies at redshift 5 to 12 or 15. All the 35 zoom-in regions include thousands of halos in there. The mass resolution is from 100 to a few thousand solar masses, and the spatial resolution, at best, we can reach parsec or even sub-parsec in the densest regions. So we have published a number of results based on these simulations, including the galaxy scaling relation, like the stellar mass halo mass relation, stellar mass function, luminosity functions, the clumpy morphology of these high redshift galaxies, and we also do full dust radius transfer calculation to study the dust attenuation, RX beta relation, so on and so forth. This is the new results on the escape fraction, particularly. I will talk about it in this talk. What we show here is the sample average escape fraction. The sample average in all the galaxies in our simulated sample as a function of halo mass on the left and as a function of stellar mass on the right. So just a note, we are not fully converged with resolution yet, but the trend of the escape fraction as a function of stellar mass or halo mass seems to be consistent between different resolution. The first result is basically the escape fraction can reach 20% at the stellar mass around 10 to the 8 solar masses. Even this is without binaries. I want to play this back and forth. If you look at the binaries, if I include binaries, binary only enhance the escape fraction from 20% to 25%. It's a weaker effect, but still something. It still has a moderate effect, but not as dramatic as we previously find. I will mention the reason in a minute. And also, the escape fraction decreases at the both ends, both at the high mass end and the low mass end. This is just an example. I want to briefly discuss why the escape fraction can reach 20% in some of these galaxies. So this is one of the examples from our simulations. A star-forming galaxy with stellar mass 10 to the 8 solar masses, and also this galaxy has the escape fraction of 20%. So the left panel here shows the galactic scale gas morphology. Basically, all the escaped ionizing photons come from this region A, marked by this white dash box. So the right panel is zooming in onto this region. The white point here shows all the stars between 3 million years to 10 million years old. And the color points show stars younger than 3 million years. The color coded by the stellar age in the middle panel. On the right panel, the colors represent the escape fraction of individual stars. So we see there's a kiloparsec scale superbubble, presumably blown up by the supernovae going off from this star 3 to 10 million years old. At the edge of the superbubble, there's a compressed, dense shell. The shell is forming stars and also accelerated along some direction, as you can see from this age gradient at the edge of this superbubble. So the interesting thing is, some of these young stars, although they're still younger than 3 million years old, they're already inside the superbubble. So these very young stars can have very high escape fraction. On average, in our simulations, about half of the escaped photons from stars younger than 3 million years old, just by this case. So this is also explain why binary have a weaker effect, because the binary stars do not play a significant effect younger than 3 million years old. So this is just some more quantitative analysis about the key physics in the escape fraction of ionizing photons. I don't want to go through too much detail in this diagnostics, but this one shows in regions you leak ionizing photon efficiently, you need supernova feedback to pre-clear the sight lines. So supernova feedback is very important to clear the surrounding of young stars. But if you also look at the column density distribution of neutral hydrogen with and without photonization from stars, this is the difference you can see. So this indicates photonization from young stars. For example, like those collectively formed in the superbubble, the photonization from these stars also play a very important role in ionizing the sight lines for ionizing photon to escape. So this just put everything together. Supernova and photonization from stars are both very important in driving the escape fraction of ionizing photons. So I want to briefly explain why there's a mass dependence as well. So on the left panel here, I re-show this escape fraction function of stellar mass. On the massive end, this is just dust attenuation. On the lower mass end, we think this is a combination of inefficient star formation and feedback in low mass halos, plus the CDM of these low mass galaxies are cooler or lower temperature. So collision ionization is very less efficient. Most of the CDM is neutral around these galaxies. So this is just a new result we submitted recently to investigate whether, since we can resolve globular cluster formation in these simulations, we want to understand whether globular cluster can provide extra ionizing photon, or whether the globular cluster have a higher escape fraction. But the quick answer is no. The globular clusters do not have higher escape fraction than other non-cluster stars in this galaxy. So skip this. some of the current work I did with, this is the work I recently did with Aaron Smith, and still in preparation, but we start to investigate Monte Carlo radial transfer of Lyman alpha on one of the Lyman continuum leakers. So this is the same galaxy I showed you earlier, but if you look at the Lyman continuum leaking region, the right panel here shows the Lyman alpha line profile. Also, we're updating the fire simulation prescriptions. We're currently working on the Fire 3 implementation, which is better supernova feedback, better treatment for the radiation hydrocoupling, and so on and so forth. So we will keep investigating the escape fraction with new generation of the cosmological zooming simulation we've been looking at. But just to summarize, I introduced the high-redshift fire product, which is a number of cosmological zooming simulations of galaxy at this epoch of reionization. For this work, we find the escape fraction peaks around 10 to the 8 solar masses in stellar mass, can reach an escape fraction of 20%. And there's a mass dependent of the escape fraction on the high mass entities because that's attenuation, on the low mass entities because of the inefficient star formation feedback. We're still not fully converged with resolution, and it's also sensitive to the subgrid recipes we use in these simulations. So we need to understand this better. Stay tuned for the next generation of these simulations. I'll just stop here and take questions.
Okay, thank you. So Xiaohan Wu asks, have you run any sims without dust so as to isolate the effect of dust absorbing ionizing photons?
We run this in post-processing. In the fire simulation, we don't trace dust grain physics explicitly. We just assume like 40% of metals are in dust grains. We do the test in post-processing without dust attenuation. It's shown in the paper. So what exactly the question is?
I think, well, yes, I think you addressed that question.
Yeah.
So Laura Somovigo asks, what is the scatter and number densities among the clouds in your simulations? How does it affect the plot related to the cloud's dispersal times that you were showing?
The scatter and number densities. Oh, number density, gas density among clouds in your simulations. We don't think we look at that explicitly, but I think the approximate answer is if we look at the star forming gas density, that's basically there's order of magnitude dispersion. So yeah, we have to check that. We don't know for sure at this point, but there's a large dispersion of or magnitude.
So Rohan Naidu asks, can you talk more about resolution effects? Do you expect a turnover towards the highest masses, even in your highest resolution runs?
Yes, there is already a trend in the higher resolution runs that the escape fraction decreases above 10 to the 8 solar masses in stellar mass. I think it's a promising or reassuring.
Okay, Max Gronk asks, you commented on the non-convergence of F-escape. Is this related to the non-convergence of H1 in the CGM discussed in different studies? I.e., is F-escape as a function of R converged if you take a smaller R around the star-forming regions?
Yeah, I think it is kind of close. The typical effect of lowering the resolution in our simulation is make things smoother. So especially in the CGM, there are column densities. There's a large distribution, a broad distribution of column densities in the CDM. So if we make things smoother, the higher column density sidelines will mess up with the lower column density sidelines. So the lower column density sidelines will be under-resolved So effectively, you lose a number of lower quantum density sidelines just because of the resolution effect. So I think that's the dominant reason why going to lower resolution, we see smaller escape fraction.
Okay, thank you. So you have a number of other questions to address on Slack. So last time we skipped over Joe Lewis. That was a technical problem on our end, not his, so we apologize for that. He's going to tell us now about the extinction and dust escape fractions in RHD cosmological simulations of reionization.
Hello, everyone. It's working now, I guess, right?
Yes.
Okay, great. So hi, everyone. I'm Joe Lewis from Strasbourg, and I'm going to talk to you a bit about some work I've been doing implementing dust physics into Ramses Cudaton, which is our cosmological RHD simulation code, and show you some brief insight into where this might lead in our next simulations, next big simulations. So to quickly motivate this, I've prepared these simple constraints on dust mass as a function of stellar mass that I've taken from two papers here, just to illustrate that at redshifts higher than 5, there's mounting evidence that we have quite a lot of dust mass in these massive star-forming galaxies, but also the dust mass is quite high relative to the stellar mass. So the question obviously is, what does this do to reionization? Because this is not something that's often been considered in large-scale cosmological simulations of reionization, and it could have considerable effects on the role of various galaxies, for example, in the photon budget and the importance of these different galaxies. So just jumping straight to it, the model we've implemented in Ramses Cudaton is a physical model by Yoann Dubois. The paper associated is not yet released, unfortunately, so I can't show you that, but I can go over some quick facts here. So the dust in our new code assumes a solar composition metallicity at an average grain size of 0.1 micrometers. We track both dust creation and destruction that happen in the Ramses part of our code, which is on the CPUs during our runs. And I've also added dust absorption that happens in the radiative transfer step in the Aton part of our code that runs on GPUs. So just to briefly outline the dust creation methods, which are both ejection from supernova, condensation of a portion of the metals ejected from supernova, and accretion of metals, of grains in metal-rich gas, dust grains in metal-rich gas. Dust destruction happens both via thermal sputtering in hot, dense gas and in the inertial shocks produced by supernova. So I think that's quite classical, but the important thing is we do this on the fly during the simulation, and we have no post-processing in this regard. So I guess I have to jump straight into some results to convince you that this actually works in some way. So here I've prepared the average dust mass to stellar mass at various times from a smallish box. So that's a 16 megaparsec box against the constraints that I just showed earlier. So this is a run that was tuned to be fairly dust heavy. So it actually is above some of the upper limits you see there in blue. But all in all, it's quite good, and it fits into the middle of the locus. So what we can also do here, passing on some stuff, is compare the same result to things from semi-analytical modeling, such as in the Popping 2017 paper. And actually you can see that we satisfy some of these constraints quite in a similar manner. Our dust mass to stellar mass ratio is quite similar at various times. This also lines up quite well with the semi-analytical models of Vigen 2019, but I don't have the plots to show that. One of the more interesting things we can do, perhaps, is look at the slope of the UV continuum in our simulation, both when accounting for reddening due to dust in galaxies and not. So the blue curves here on the left and the right at two different times show you the average beta as a function of magnitude. The full curves are when we account for reddening. The dashed curves are when we don't. And these black points you can see are taken from our averaged constraints from Finkelstein 2012. So the main thing I guess you can see is, well, first, both of the data sets are quite highly scattered. But the addition of this reddening from our dust does make our averages more realistic, though perhaps there's a little bit too much reddening going on. The trend that we get from minus 16 magnitude to about minus 19 is quite encouraging, because it does seem to echo what the points are doing here. Okay, so maybe I can move on to some more predictive stuff, because this means that in the same box we can look at extinction and the ultraviolet luminosity function. So on the left, I'm showing you a simple histogram of magnitudes, both with and without extinction due to dust. And the red zones just highlight the effect of the extinction, which you can see is actually in quite considerable for galaxies that are brighter than minus 20. Again, this is a quite dust-heavy run. So in a more maybe conventional way of looking at things, here's the luminosity function of this same 16 megaparsec box against the points from Bounds 2017. And you can see in the lower right-hand corner the same red zones that denote the effect of extinction. You can see again that actually there's quite a remarkable effect on the UV luminosity function that's possible. So moving very swiftly on, I've got some time to talk about the escape fractions through the dust that we simulate. So when I talk about escape fractions here, I just want to talk to you about the dust. So I'm computing the optical depths due to dust along lines of sights from star formation sites to the R200s of galaxies. And this is the average over the galaxies as a function of their halo star formation rate at various times. So one of the kind of remarkable things is it doesn't change much over the various redshifts. But I think the main takeaway for me here in this very quick talk is that already in such a small box, and for galaxies that don't exceed 10 to the 9 solar masses of stellar mass, you're getting escape fractions due to dust that are lower than 10%. So you can imagine that with more massive galaxies, we could possibly get even lower escape fractions. Though obviously this is to vary with the exact calibration and tuning of the dust model, which may be improvable still. But this could have dramatic repercussions for reionization, making these massive galaxies with more than 10 to the 9, 10 to the 10 solar masses of stellar mass not as important as you might think otherwise in comparable simulations. So in conclusion, we've implemented a physical dust model in the RHD cosmological simulation code Ramses Coudeton. We can produce dust masses which are compatible with several semi-analytical model results, but also with constraints from ALMA, for example. The UV continuum slopes that we get from doing this are actually more realistic now that we've included reddening from dust, though again, this is probably susceptible to some kind of calibration in terms of resolution and parameters of our model. Finally, we showed that dust in our simulation can have considerable effects on the ultraviolet luminosity function, as well as on the escape fractions of massive galaxies, potentially rendering them much less important than you might otherwise think for reionization in our simulations. So that's it for me. If I have a little bit more time left, I'd just like to mention that this is all stuff that's going to go into the next generation of Ramses Q2 simulations, the Cosmic Dawn project, which should run sometime later this year. Thank you.
Okay, so Tom Toons asks, what are the largest error bars on beta in the simulations?
In the simulations. So what actually happens is there are a few galaxies that have much lower dust content, and they seem to almost follow the trend of the no dust average that I'm showing here. And this is, as I said, quite a dusty box, this example that I've given. So it actually overshoots quite a bit in the other way. So that's why you get the large scatter, if that makes sense. Tell me if it doesn't, I'll try and convince you more.
Ashwin Vijayan says, nice talk. How much evolution in the dust to metal ratio do you see across redshifts?
So that's a very interesting question. We do not see that much evolution, though we haven't taken anything down past z=4 so far. What does seem to happen is you get like an S curve in the average DTM. And what seems to happen is the S moves to the right as a function of stellar mass. If that, I have no curves currently in this PowerPoint to help you, but so what that means is, what does that mean? That means that slowly you get a higher fraction of galaxies with high DTM. So this is something, the next question, I can read them. I kind of jumped
okay, yeah, so yeah. Do you want to move on to the next question? Or?
Okay. So with regards to resolution, this is something we haven't played that much yet with just concerning the dust. So this is the resolution of our previous big box, Cosmic Dawn 2. And so though it does resolve the smaller atomic cooling halos, it does it just only. The next generations that have twice that resolution, and most of this dust physics is happening in the more massive galaxies anyway, which are quite well resolved.
Okay, thank you. And I think we have time for one last question from Dennis Bergarella. Dust has a strong influence on the UV emission of galaxies. Do you expect an effect of the galaxy mass function?
Could you be more precise exactly? Oh, on
yeah,
the,
okay. Yeah, on the galaxy mass function.
Yeah, I mean that's possible. That's possible. It depends on how you correct for it. Yeah, I haven't looked into it exactly, so I can't. I'm afraid to say something wrong. Sorry, I can't be more specific.
All right, thank you. So we'll return now to the normal schedule. So Harley Katz is going to tell us about new methods for probing Lyman continuum leakers and Reionization-Epoch analogues with nebular and IR emission lines.
Great. So thank you so much to the organizers for giving me this opportunity. My name is Harley Katz. I'm currently a visitor at the University of Oxford. And over the next 10 minutes or so, I'm going to be presenting a project that we recently put on the archive about how we're comparing our radiative transfer simulations with observations. So there's sort of two main questions I'd like to address with this talk. As you've heard a number of times, studying galaxies directly in the epoch of reionization is incredibly difficult for a number of reasons. So a lot of us focus on what we call analogues at redshifts less than 6. But I think one of the open questions about these types of systems is whether or not these analogues are actually truly representative of galaxies in the epoch of reionization. I think there's a subset of these analogues, which are the Lyman continuum leakers. And as you heard earlier this morning, we actually only know a very few of these. Many of them tend to have escape fractions lower than what you would expect you would need to actually reionize the universe. So the second question we'd like to address is how can we better identify these Lyman continuum leakers across all redshifts? Now, there's a number of different methods for identifying Lyman leakers. A bunch of them are listed here on the left. I'm not going to go through all of them, of course, but one of the most popular methods is looking for galaxies which have a high ratio of O32. And you can see that's, as we define it, it's a log quantity of a bunch of oxygen-3 emission lines divided by a bunch of oxygen-2 emission lines. And the general idea behind this is that you can kind of imagine a very idealized molecular cloud, which has a 0 escape fraction. You have your ionizing sources embedded, and then as the ionizing radiation is penetrating through this cloud, it's creating shells of regions that emit in oxygen-3, oxygen-2, and oxygen-1. Of course, you can imagine a separate scenario where instead of having the radiation being bounded by the cloud, the radiation actually breaks through. And then when that happens, you actually break in and eat away at the oxygen-1 and oxygen-2 emitting regions, which lowers your ratio of oxygen-3 to oxygen-2. So that's why, in general, people tend to focus on these types of galaxies. One of the big questions, though, is because we can't directly observe this ratio at redshift greater than 6, is whether the leakers that are reionizing the universe are actually represented by this type of interstellar medium physics. Now, in order to actually compare with observations, we need to run simulations, of course. And so what I'm going to be doing is introducing a suite we call the Aspen simulations. And these are cosmological radiation hydrodynamic simulations. So they include a 7-species non-equilibrium chemistry model. Most importantly, the radiation is coupled to the molecular hydrogen in the simulation. We're using 8 bins of radiation transfer all the way from the infrared up to the helium-2 ionizing, including things like the Habing band and Lyman-Warner. In order to study the interstellar medium, we need quite high resolution. So these simulations resolve down to about 10 parsecs in the interstellar medium. And most importantly, because we know the density, temperature, metallicity, and inhomogeneous radiation field in the interstellar medium, we can actually post-process every single cell with a photoionization code like Cloudy to predict things like emission lines and nebular continuum. And if you do this properly, you can see on the right, you can create these beautiful maps of things like oxygen-3, 5007 angstroms. You have your carbon-3 emission lines, which we've heard about, oxygen-2 emission lines. And just for this one galaxy, there's about 3 million Cloudy models that go into it. And we do this for the more than 1,000 galaxies at every single snapshot we output in the simulation. So onto the results, we can directly look at whether or not the leakers in these simulations actually have high ratios of O32. So what you're looking at on the x-axis is the O32 for the simulated galaxies shown as the black points versus the Lyman continuum escape fraction shown on the y-axis. If we simply take an O32 threshold of 0, we find that for the galaxies that have an O32 higher than this value, about 11% of them are actually leaking Lyman continuum radiation. In contrast, galaxies that have lower O32 ratios, only about 1% of those are actually leakers. So in general, this basic physical model holds that you would expect there to be a bias that high O32 galaxies are Lyman continuum leakers. You can compare this with observations shown in cyan and magenta, and you can see that the regions where the leakers that we observe populate roughly are consistent with those from our simulations. Of course, we tend to find a number of galaxies in our simulations, the ones like focused down here at the bottom, which have high O32 but very low F escape. So what we can take away from this is that O32 seems to be a necessary condition for Lyman continuum escape, but it's insufficient for high escape fractions. And I think one of the questions is why can you have galaxies with high O32 but low F escape? And I think there's two pieces of physics that are coming into play. The first one is viewing angle. So if we just focus on an individual galaxy and put ourselves right at the center, we can create a mole-wide projection of the neutral hydrogen column density. So everywhere you see a bright region is where the column density is like roughly optically thick, and everywhere you see a dark region is where Lyman continuum radiation can escape. So depending on which sight line you have, F escape is the global F escape is an angle average quantity, but of course that's not what we observe with our telescope. So you might just be in a situation where you have high O32, which is not really impacted as much by viewing angle, compared to F escape, which is very impacted by viewing angle. Now, in addition to viewing angle playing a role, there seems to be something going on in the interstellar medium that can actually cause high O32 but low F escapes. So I'm showing you examples of two galaxies. This one here on the top has a high F escape and a high O32, but this one here on the bottom has a low F escape and also a high O32. And if you just look at the density projections here in the second column, you can see the top one has a completely different morphology than the one on the bottom. This one is clearly being disrupted by feedback. You can actually see the low density channels through which radiation can escape. In contrast, the galaxy at the bottom is much more compact. And these galaxies have very different morphologies, stellar masses, ionization parameters, and metallicities, despite having roughly similar dark matter halo masses. So what this goes to show you is that there's very complicated physics in the interstellar medium based on all of these different properties that can actually drive high O32 and low F escape, in addition to things going on with viewing angle. Now, hopefully I've convinced you that O32 is a somewhat useful property to constrain the Lyman continuum escape fraction. The question is are these galaxies at, for example, redshift 3 and redshifts below a half that we've been observing directly Lyman continuum escape actually representative of the high redshift population? And I think one of the best ways to actually answer that question is to look at things like strong line diagnostics. So I'm showing you an example here on the left. On the x-axis is R23, and on the y-axis is O32. The simulated galaxies are shown as the black points, and I've highlighted the leakers in our simulations as the bright red points. Now, there's low metallicity galaxies that were studied by Nakajima et al. These are shown as cyan. These are the ones that are not, sorry, the cyan ones are leaking, and the magenta ones are not leaking. And you can see that in this R23-O32 plane, the regions that the observed galaxies at redshift 3 populate are actually completely consistent with what we see in our simulations. And in fact, there's no really good way to separate leakers from non-leakers on this plane. Now, this one diagnostic would suggest that, yes, these redshift 3 galaxies tend to be good analogs of galaxies well deep into the epoch of reionization. But we can actually go further. We can look at a vast number of diagnostics. I'm not going to go through all of them, but here's the standard nitrogen 2 BPT diagram, the S2 BPT diagram, as well as things like the mass excitation relation. And over a number of these strong line diagnostics, we're finding surprisingly good overlap between where redshift 3 to 4 galaxies exist and what our simulations are predicting for galaxies at redshift greater than 6. So I'm fairly confident that most of the lower metallicity galaxies we have that we're studying at Z3 are actually consistent with those in the epoch of reionization. Now, the second question we wanted to answer is, are there better ways of actually identifying these Lyman continuum leakers? And the reason we want to do this is because, as I showed you with this O32 diagnostic, only about 11% of them that have high O32 are actually Lyman continuum leakers. So what we've done is, because we've measured so many of these different emission lines in our simulation, we can actually run some simple logistic regression models using something like L1 regularization to try and predict which combinations of lines are actually the most predictive of leaking Lyman continuum radiation. So I'm just showing you a few examples of these logistic regression coefficients compared to the different lines. Just here's about 9 of them. And what I want you to focus on is whether or not the logistic regression coefficient is positive or negative. If the coefficient is negative, it means that that line anti-correlates with leaking radiation. In contrast, if it's positive, it means that it positively correlates with leaking radiation. And for the most part, the two most important lines that we see from these logistic regression models is the carbon-2 158 micron line and the oxygen-3 5007 angstrom line. Now, as you've heard earlier in this session, F-escape is a feedback regulated quantity. So in order to actually identify Lyman continuum leakers, really what you need is lines that are going to, one, correlate with the presence of feedback. So for example, as you're looking here at density temperature diagrams, we have our oxygen 3 line is actually populating the regions of ionized gas that's seemingly being impacted by supernova feedback. Hence why oxygen 3, 5,000 angstroms, correlates with high Lyman continuum leakage. In contrast, our carbon 2 158 micron line is being emitted mostly from the neutral gas regions. And of course, if you have neutral gas, that's going to inhibit F-escape. So the positive and negative correlations are directly related with where these regions populate, where these lines populate in the interstellar medium. Now, you can ask, how good are these logistic regression models at separating leakers from non-leakers? So what you're looking at here on the x-axis is the carbon 2 luminosity, and on the y-axis is the oxygen 3 5007 angstrom luminosity. Once again, the cyan points are our leakers and the black points are our non-leakers. And the background color map shows you the probability given by the logistic regression model that the galaxy is a leaker or a non-leaker. And this sort of white dividing line shows roughly a 50% probability. And you can see visually that this logistic regression model does a fairly good job at separating leakers from non-leakers. Unfortunately, very few surveys actually have measurements of both infrared and optical emission lines. So in order to try to directly compare this with observations, what we've done is we've trained a different logistic regression model where we've replaced the oxygen 3 5007 angstrom line with an oxygen 3 88 micron line, which is of course also in the infrared. Now, since our logistic regression model didn't pick this line out, it's going to be slightly less accurate, but you can see from this plot, it does a relatively good job still of separating the cyan point leakers from the black point non-leakers. But of course, now that both of these lines are in the infrared, we can directly compare to observations. So this magenta points represent galaxies from the Dwarf Galaxy Survey. And what's interesting is that they tend to straddle these white regions, which means some of these galaxies we actually predict to be leakers, while many we predict to be non-leakers. Unfortunately, we don't have measurements of the Lyman continuum escape fraction from all of these galaxies, but hopefully follow-up observations can confirm or refute my model. However, as you heard earlier this week, one of the most interesting things we can do is that we actually have a number of galaxies directly in the epoch of reionization that have oxygen 3 and carbon 2 emission lines. So we can make predictions for whether or not those are leakers. And what we find is that this MAX 1149 JD1 galaxy at redshift 9.1 is our most promising observed known galaxy to actually be leaking Lyman continuum radiation. So thanks so much for giving me this opportunity, and I'll leave up my conclusions.
Thank you. The questions for Harley. Okay, so Tom Bax asks, for these galaxies in the EOR, what is the time dependency of the F-escape? Does this vary significantly with time, such as Arata et al. 2019, or is it relatively constant per source?
Yes, so in the simulations, the F-escape values fluctuate quite considerably. I mean, on very, very short timescales, we're talking mega years. The good thing is, though, is that from our simulations, we also find that things like the carbon 2 and the oxygen 3 emission lines are also going to fluctuate with the properties of the interstellar medium. So a lot of that should be encapsulated in sort of what time you're actually observing the galaxy, what those emission line luminosities are going to be.
Okay. Gerald Melema asked, in your last figure, why are the EOR galaxies in their own unique location, which does not overlap with your models?
Yeah, that's a really good question. It's simply because the EOR galaxies that we know about are just much more highly luminous. And this is not particularly surprising because with high redshift galaxies, you're of course going to observe the much more bright galaxies. Our simulations, the box size isn't big enough. So you can see the brightest galaxies only have luminosities of around 10 to the 40 ergs per second. So really, we just need a little bit of a bigger box size in order to probe these much higher luminous galaxies.
So Livia Vellini asks, very nice talk. Do you plan to include also oxygen-3 52 micron in your predictions? Could it be useful to complement oxygen-3 88 microns as their ratio depends on gas density?
Yeah, so we actually do predict oxygen 352 microns. You can kind of see it in this plot here in the top right corner. So basically what we were trying to do is that the reason why we applied L1 regularization is because we wanted to try and come up with models that have the fewest number of lines, because we figured that would make things easier for observers. As you add more and more lines into the logistic regression models, our ability to classify galaxies as leakers versus non-leakers gets better and better. And that's unsurprising because, as you can see, the regions where you have oxygen-3 52 microns, as you mentioned, are different from oxygen-3 88 microns. So yes, we do have like much more detailed models, but I focused here in this talk just on the ones with 2 lines.
Okay, thank you. So you have a number of other questions on Slack, but we need to move on to our last talk, which is Andrew Emerick, star-by-star cosmological simulations of the first galaxies and their chemical evolution.
Great, thank you. I'm happy to be here today, and I guess virtually here today, and I just wanted to thank all the conference organizers for giving me the opportunity to talk and present to all of you, and to be able to hear what's been a really great collection of talks over the past few days. I've learned quite a lot, and it's been great to have the opportunity to hear from people I otherwise wouldn't have been able to without this conference. So my name is Andrew Emerick. I'm currently a Pasadena postdoctoral fellow in theoretical astrophysics, jointly appointed at Carnegie Observatories and Caltech. And what I wanted to do today was introduce to all of you a set of simulations that are currently running that I am very excited about, and my collaborators and I are both very excited about. But as these simulations are sort of still very much ongoing, just as a warning, this will be a mostly results-free talk, but I promise there's still cool images and a movie at the end if you stick through. So my main motivation for carrying out the simulations I'm going to introduce to you is a little bit of a departure, I think, from what most people have talked about so far at this conference. So I'm mostly interested in trying to understand what the detailed chemical fingerprints are of the very first galaxies in the universe, and how we can possibly try to understand the origin of those fingerprints and how they map to observed stellar abundance patterns in galaxies in the local universe. So it's a bit of a departure because it's sort of the near-far connection and focuses on stellar abundances, but I think it's really important and well connected to what a lot of people here find interesting, because in order to understand this, you really have to have a good detailed understanding of the metal history and evolution of metal enrichment in the universe from the very first stars through ionization until today. And so in detail, again, the questions I'm interested in are, how are the stellar abundances of local group dwarf galaxies potentially representative of the very first galaxies? Or is it the case that the very first galaxies and their chemical signatures are better represented in stars in the Milky Way halo? And by understanding what those signatures are, can we know, which stars in the Milky Way or again the local group are remnants from the very first structures in the universe? And again, related to that, what are the signatures, unique signatures of stars formed directly from POP3 star enrichment, or most purely from POP3 star enrichment, and from both core collapse supernovae from population 3 stars and parent stability supernovae from these stars. And in general, what physics really drives the mixing and evolution of metals in gas, in the ISM, CGM, and the IAGM at high redshifts, and how does that play into driving the scatter and observed stellar abundances? And part of the reason why I'm so interested in doing this is because I think you can think of metals as nature's tracer particles, and so this is sort of illustrating that to some degree. This is a plot of the magnesium to iron ratio as a function of metallicity. And I see now I've conveniently lopped off the units or the numbers on the x-axis, but I think the point is still a bit clear, which is that there are differences in how and what stellar abundances look like in different galaxies. Shown here, you can see in color the different dwarf galaxies in the local group as the gray points, the stars in the Milky Way halo itself. And encoded deeply in these stellar abundances in both the median evolution of these abundances and in the scatter of these abundances, I think is a lot of details about galactic evolution to drive both the median trends here and the scatter in these abundances. And so it'd be particularly useful and exciting if we could take the observed stellar abundance patterns that we see today to learn something about the evolution of the first galaxies. And with these simulations, I'd like to be able to attempt to make that connection and do a lot of other interesting science with that as well. But part of the problem here, just to illustrate this, is that galactic chemical evolution is quite messy. So this plot shows an example of this with the sort of the median metallicity evolution of 3 different dwarf galaxies at high redshift with 3 different star formation histories, shown as the solid line, and then the scatter about that median in the shaded line, and then the dots represent the stars formed in those galaxies. And the point is that depending on the star formation history of galaxies, depending on the local environment, the properties of gas, and all the feedback physics that you include in these simulations, that could drive very significant differences in the median trends and the scatter and evolution and the metal content of these galaxies. And that's true for the total metallicity, but I'm also very interested in how that is true independently for individual metal species, which may originate from different nucleosynthetic sources like stellar winds or core collapse supernovae, type 1a supernovae, AGB winds, and our process enrichment as well. And so, with all that in the context, again, the questions I'm most interested in, which I think are probably interesting to other people as well, I hope, are, what are the chemical fingerprints of the first galaxies? How is the gas from these first galaxies, the ISM and the CGM around them, and also the IGM, enriched in the early universe? And again, what drives the variety of stellar abundance patterns seen in galaxies today, both the scatter and spread within an individual galaxy, and also the galaxy-to-galaxy scatter, particularly for the very, very low mass dwarf galaxies that we see today. And what are the unique observable signatures of both POP3 and POP2 enrichment at high redshift? And so what I wanted to introduce to you today is what is, to my knowledge, I think, someone please correct me, is the first star-by-star cosmological simulations of the first galaxies for both POP3 and POP2 star formation. And so these simulations are ongoing, and they're run using the adaptive mesh refinement code ENSO. And again, the first set of cosmological simulations where we do a star-by-star approach, which allows us to get detailed stellar feedback and detailed galactic chemical evolution from these galaxies. And this image here, which I'll sort of explain more later, is just a teaser of the simulation that's currently ongoing. I happen to pick redshift 19 for this image because that happens to be where the simulation is now. But what you're seeing here is just the full box projections of the gas number density on the left and the gas temperature on the right, overlaid in both cases with the oxygen enrichment on the left from the POP3 stars, which are shown as black points, and also the ionizing heating from these stars, as I do follow full radio transfer in these simulations. And so the gory details of this is that we have star formation with POP3 and POP2 stars. So we're following POP3 stars from 1 to 300 solar masses individually, randomly sampling an IMF with a characteristic mass of about 20 solar masses. And above metallicity threshold, which is driven by the carbon and iron abundance in the gas, we can form POP2 stars, which are again sampled randomly from an IMF. And followed individually for stars between 2 and 120 solar masses. And below 2 solar masses, I'd sort of aggregate the stars together into a single star particle, mostly because we only plan to run these simulations to about redshift 7, which is less than the lifetime of one of those stars. And we fold that in with a Grackle non-equilibrium chemistry and cooling, with a UV background, an updated Lyman background, and a self-shielding model of the gas against the UV background. And with the individual stars, we can do star-by-star multi-channel stellar feedback. So for each of the stars, we're tracking their evolution and whether or not they explode as core collapse supernovae. For the low mass stars, we actually evolve them into white dwarfs and have a sort of realistic way of capturing them as type 1a supernovae. And in the POP3 stars, we have both core collapse supernovae and pair instability supernovae from the high mass POP3 stars. For everything, we have stellar winds with a sort of reduced velocity approximation to make the computation a bit easier, and HB winds from low mass stars. And I think what's most exciting and relevant, again, for the area of reionization is that we're also including ionizing radiation tracked with an adaptive ray tracing radiative transfer method for both hydrogen and helium. And on top of that, using an optically thin approximation, we're following Lyman burner, FUV, IR, and optical radiation from these stars. And what I'm most excited by, and I'm almost done, is that we're tracking, in addition to all the feedback physics, 10 different individual metal species, tracking different nucleosynthetic sources from all of these stars, having individual metal tracers for all these metal species, and a separate set of metal tracers for all these species, tracking the contribution to these fields from POP3 stars themselves, for a total source of 29 metal tracer fields, because we also include tracers for each individual source, like supernovae, POP3 core collapse supernovae, POP3 pair instability supernovae, and a type 1a model with 4 distinct sources to try and distinguish between origins of different type 1a elements. And in addition to this, an R process model for R process enrichment. And almost last slide. So the full box, we have a fiducial simulation set with the full box simulations of a co-moving megaparsec run to about 0.5 to 1 parsec resolution of the finest cells, run with and without pair instability supernovae. And then we will have a higher resolution zoom-in simulations following individual dwarf galaxies with different virial masses. And so with that, I will leave you with the cool movie of the simulation so far, and happy to take questions. Thank you.
Okay, questions for Andrew. Sarah Bozeman asks, what assumptions are you making for the population 3 and population 2 IMFs, and do they have metallicity dependence?
Good question. So the POP3 IMF, so in both cases, the IMF is not metallicity dependent. For the POP3 IMF, we just assume an exponential IMF below a characteristic mass of 20 solar masses and a saltpeter IMF above that. For the POP2 IMF, we just assume a Krupa IMF.
Other question. Okay, Gerald Melema, why do you select these 10 elements to include?
It's a great question. So we try to, ultimately, right, we're limited to the number of elements we can follow because it gets expensive, both in sense of memory. So these 10 elements was the sort of the best, the most we could do with as few elements as possible, if that makes sense. So they track different yield sources quite well. So there's, for example, barium and strontium we picked because they're good tracers of the S process and also a little bit of the R process. We have different elements from the alpha elements like magnesium and oxygen from core collapse supernovae, iron from type 1a supernovae, and also carbon and nitrogen, which are sampled from a bunch of these sources. And also, the elements we picked are generally those that are most well observed in either stellar abundances or in gas phase abundances.
Anna Schauer says, very nice talk, and I look forward to the results. Did you consider initial conditions with a non-zero streaming velocity?
Good question. We have not, mostly for the sake of simplicity. But I think, yeah, after listening to your talk, that's clearly something we should consider.
Okay, and Tom Tunes, since you simulate star by star, how does the IMF enter? Do you randomly sample from it?
Yeah, so the IMF, we assume an IMF, and then when a gas cell hits the right star formation criteria, then we randomly sample the IMF and deposit individual stars. So in many ways, it's the star formation routine works the way that anyone's star formation routine works, and IMF assumptions work. It's just that instead of a simple stellar population, we actually break that simple stellar population into individual stars in the simulation.
Okay, and Stephen McCandless, is the H2 rotational vibrational population fixed at thermal, or is it affected by the FUV pumping?
It is not affected by the FUV pumping. No, that is not something we include.
Okay, and I think we have time for maybe one last one. Dan Ko, you said no results yet, but anything preliminary? When did the first population 3, population 2 stars form? Any redshift 19 galaxies to speak of?
So you're looking at all the results that I have right now as I made this movie this morning. So it looks like the first stars in this box were forming at around redshift of 23, 24. I have not run any sort of halo finders on this yet to see exactly where they're forming and what kind of properties the dark matter and the gas are in those regions yet.
Okay, yeah, one last question on Slack to address. So that concludes the talks, and thank you to all the speakers. Do the Steves have any concluding remarks?
Yes, I just wanted to thank everybody again, in particular all the speakers, obviously the SOC, but especially the LOC, who have done the unenviable job of uploading all the videos and moderating all the Slack channels. So just to name them, because I realized we didn't do this at the beginning, there was Michaela Bagley, Luke Conaboy, UC Kusisto, Rebecca Larson, Ashwin Vijayan, and Will Roper. I hope you all agree with me, and I think some of the other people, that the entire meeting has gone really well, surprisingly well, in fact, given how rushed it was putting it all together. Sorry, hopefully people can still hear me. I just noticed that my internet has dropped out a little bit.
We can hear you.
You're good.
Great. I think the main thing that I wanted to just end on is that I hope that what we've done this summer is something that can be repeated in the future. And I know there was lots of discussion today during the discussion sessions about how we might be able to take this forward in the future. So lots of ideas have come out here. But I think, I mean, hopefully we won't be in the same situation now that we are in next year. But I think there are still good reasons for us to do this type of virtual conference. So in particular, people who can't afford to travel or have caring responsibilities, and many other reasons. So for this reason, I would really like to see at least this kind of summer meeting going ahead in the future, but maybe we can even do other things. I mean, there was lots of great suggestions in the Sazerac feedback channel, which I hope we will explore. We will leave the Slack group open. Obviously, there are lots of questions on there that still need answering. People can still interact there. Obviously, all of the talks will be on YouTube and on our website, so they should be there for as long as we need them to be there. And I think that was a bit about it. And I just want to thank everybody again. I think the talks are excellent. The questions are excellent. I think the conference just went much more smoothly than I was anticipating. And I don't know if other Steve has anything to say.
Thanks, Steve. No, not much. I also have a poor internet connection right now, but I want to thank all the speakers and the SOC, and especially the LOC for running the meeting. And also a big thanks to Steve Wilkins, who had to manage the webinar, so really had to be on the ball the whole time. And I think the technical aspects went surprisingly well. And I hope that we can continue to discuss on the Slack and have a similarly successful conference or series of conferences like this in the future. So thanks everyone for attending.
So I think that brings us to the end. Good luck. I hope everybody stays safe and well, and deals with teaching and learning and researching over the next few months. And hopefully see you soon in another Sazerac or maybe a different format. And thanks for listening and thanks for joining.
Bye, everyone.
Bye.